Hi, good morning my dear students and welcome to the world of electronics. Our lesson for today is taken from lesson 1 of module 1 under ALX 1 to 3, which is semiconductor devices. The lesson tackles about diodes. These diodes are rectifier diode, Zener diode, Schottky diode, tunnel diode, Baractor diode, light emitting diode, transient voltage suppression diode, laser diode, infrared light emitting diode, photodiode, signal diode. Also included in our lesson are bridge rectifier diode, infrared sensor, 7-segment LED display, and dual rectifier diode. For your information class, diodes are among the most widely used electronic devices and electronics technology. If we try to scan any of the electronic appliances such as LED TV, if we try to scan the internal circuit of it, just like this main board of the LED TV, the main board uses rectifier diodes over here. We have also rectifier diodes over here. And at the front of the LED TV also uses diodes such as light emitting diodes. There are actually 40 light emitting diodes which are placed at the back of the screen. They are used to illuminate or to brighten the screen in order that we can see or the pictures are displayed on the screen. How about for this DVD player? The DVD player uses rectifier diodes also of this power supply circuit of the DVD player. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 rectifier diodes with 2 Zener diodes. How about for this optical pickup? We have here an optical pickup that reads and detects the information recorded on the surface of the compact disc record. So, in this optical pickup, it includes the laser diode, also the photodiode over here. Photodiode, and we have here a laser diode. Also with the CCTV. The CCTV camera actually or recorder, if we try to scan the internal circuit of that, there are lots of diodes. Also, with this camera, we have here a photodiode which will sense the image or detect that, convert that image into electrical signal surrounded with infrared LED, no? Which will illuminate the image during night time. Even this cellular phone, the internal circuit uses lots of diodes. Also, this camera is made of photodiode. Photodiode actually is used during video recording, picture taking, okay? That is how important diodes are in the cellular phone. So, the application of diodes are not only limited to these appliances. How about the sound system? The satellite decoder, the computers, the electrically operated appliances such as electric oven, electronic operated washing machine, air conditioner, even refrigerator. How about the vehicles, the motorcycles, the trucks are also using electronic circuitry. We can imagine, class, what human lives would it be like without electronics technology. So, what are these diodes? And how these diodes behave in electronic circuitries? Diode actually is a unidirectional device that conducts electric current in only one direction. Okay, let us find out. Let us make a simple circuit. a circuit comprising of a lamp that serves as a load, a diode that serves as a switch, and a battery that serves as a DC power supply of the circuit. Okay, let us connect this positive side to the end of this lamp, and the other negative terminal is connected to the end of this diode. Okay. Let us check. Okay, we have here. Now the lamp glows light, indicating that the current from this battery is circulating around the circuit. This manifests that this diode allows the electric current to flow around the circuit. However, if this diode is inverted, the bulb or the lamp doesn't glow, indicating that the current from this battery is not circulating around the circuit. That manifests that this diode blocks the flow of the current. Therefore, diode is a unidirectional device that conducts current in only one direction. Okay. Diode actually is made of semiconductor materials. Thus, diode is a semiconductor device. Semiconductor devices which are widely used for the manufacture of diodes are silicon, germanium, and gallium. Diode is a birthplace of two electrodes. Di means two, and OD is electrons. There are two electrons of this diode. That is why there are two terminals for the anode and the cathode. Diode is manufactured with two layers. The positive layer, P-type layer, and the N-type layer, with a junction between them that serves as a barrier. A pure silicon or a pure germanium could not provide polarities. It should be impaired with dopants or other elements. For the silicon, if this diode is made of silicon, to make it negative for the cathode, it should be doped or mixed with phosphorus. And to make this layer positive for the anode, it should be mixed with aluminum. So aluminum and phosphorus are impurities to provide polarities for this diode. If it is forward bias, there is an external power supply, positive over here and negative over here. This is forward bias because the negative of the cathode is connected to the negative side of the power supply or battery, with respect to the positive side also of the anode. So in this case, it is forward bias. Current can freely flow from cathode to anode, depleting or destroying the barrier. The amount of the biasing voltage or the barrier voltage here for silicon is 0.6 volts as the average biasing voltage that is needed of this diode in order that this diode will operate normally or operates at full swing. It can be operated from 0.5 volts to 0.7 volts. That is the barrier voltage, which is the biasing voltage needed by this diode. But if this diode is made of germanium, just the same, there are negative and positive for the cathode and the anode. So germanium material, a pure germanium cannot provide polarities. It should be impaired with other elements such as boron and indium to provide negative for the cathode and positive for the anode. And the barrier voltage or the biasing voltage between the two layers is around 0.2 volts as the average. It can be varied from 0.1 volts to 0.3 volts. So those are the biasing voltage for the silicon and germanium. Silicon should be 0.6 volts and germanium should be 0.1 volts. 0.2 volts for the germanium and silicon should be 0.6 volts. Okay. By the way, class, how can we identify the two electrodes of an actual diode like this? For example, this is a rectifier diode. When can we tell that this is cathode and this is anode? If we have to observe closely, there is a white band or a gray band on this side. That indicates that this is cathode terminal. And this portion is the anode. By the way, class, this is not the silicon, huh? Although this diode, which is rectifier diode, is made of silicon, but we cannot touch the silicon. This is just a plastic package made of plastic vinyl, no? The silicon actually is encapsulated with plastic. Okay. So, we can determine that this is cathode and this is anode because of the white band. But, to make it sure that this is anode and cathode, we have to test it with ohmmeter. Just set your multimeter to ohmmeter. You may use times 1 or you may use times 10. It is advisable to use times 10 since the current is lower compared to times 1 as the lowest ohmmeter range or lowest range resistance of the ohmmeter. You may use times 10 or times 100 or times 10 key or times 1 key, no? Okay, we have here, if the pointer doesn't deflect, that indicates that it is reversed bias. But if we reverse the polarity of the ohmmeter, it deflects the pointer. So therefore, this is forward bias. This terminal which is connected to this test rod, which is black test rod, is the anode. And the red test rod is the cathode. You might be amazed or confused why black should be negative. This color of the test rods are applicable only to the voltmeter DC and the ammeter DC. This should be negative and positive for these two meters. But for the ohmmeter, this should be positive and this should be negative. Because if we try to open the back of this multitester, you can see the battery. The two dry cells, AA, and the flat battery, which is 9 volts plus 3 volts, 12 volts. 12 volts actually are the internal power supply for the ohmmeter alone. This battery are not used for the voltmeter DC and ammeter DC. If we remove this battery from the multitester, there is no deflection anymore for the ohmmeter. You can no longer use the ohmmeter because it doesn't have battery. But you can still use the voltmeter, even for AC. You can still use for measuring the current, voltage. Even the DC voltmeter, you can still use, although there is no battery inside. See? So, this would mean that this battery is intended only for the ohmmeter. And we can tell that this is negative for the ohmmeter and the black test pad is positive. Because if we will try to get the continuity using times 1 ohm range, so it is advisable to always set the ohmmeter deflection pointer at 0 level. So, Set it using this ohmmeter. Set it to 0. Ohmmeter adjuster. No? 0 adjuster. For sure, to have an accurate reading. Then, see that this is the positive side because it is red for the voltmeter and ammeter. But for the ohmmeter, this is negative because this positive jack that connects the red test rod is connected to the negative side of the battery. This would mean that this is negative for the ohmmeter and this is positive. That is why when you look for the electrodes of the diode, look for the forward bias, the deflect pointer. So this is now the anode because this is positive. Anode should be positive. And this red test rod, which is cathode, which is negative, is connected to the cathode. So this should be the normal measurement of the diode. Deflect for forward bias, and it doesn't deflect, it is open, reverse bias. Okay. And now let us come to the different operations of the diodes and an electronic circuitry. Let us first have this rectifier diode. Rectifier diode is named rectifier because it is capable or it is used for converting AC voltages into DC. There is rectification as the process of conversion of AC into DC. Basically, there are three types of rectifier diodes or rectifier circuits. These are the half-wave rectifier, the full-wave rectifier, center tap type, and the full-wave rectifier, bridge type. Okay, we have here a simple rectifier circuit for half-wave. Okay. We have here a transformer. Primary is connected to the AC source. We have here the AC source. Okay. This symbol is the symbol for AC source. No? AC source. Because we are getting AC voltage at this outlet. Okay? Being connected to the primary winding of this transformer. That's why we have here. No? We have here. Then, transformer has two windings, the primary and the secondary. It is actually an step down transformer because 220 is lowered down to 12 volts. So we have here 0, 12 volts. The purpose of this transformer is to lower down the voltage. We can actually measure the voltage at this output. Okay? Using this digital meter. Set it to voltmeter range and set it to AC voltmeter. Just press this portion here to select the AC and the DC. That is DC. But when it is AC, there is an AC symbol. Measure the voltage at this primary winding. Not yet connected. It is not yet connected. Okay. Okay. It is 239 volts AC. Distributed by the Sulico company. And at the output, secondary, it is 12.94 volts. 12.94 volts. To prove that it is AC being outputted at the secondary, we can use an oscilloscope. Okay, we have here okay. That is now the AC waveform. That proves that the voltage being transformed in the secondary is still AC. That is why we are using AC voltmeter to measure the voltage at the secondary. So this voltage should be converted into DC. So we will use, or we will first conduct the first basic rectifier circuit, which is the half-wave rectifier circuit. A half-wave rectifier circuit uses one diode. With resistor that served as the load resistance. Okay, we have here a capacitor. So let us not connect yet this capacitor. B. Okay. At first, this one muna. So, single diode. The anode is over here to be connected to this this one is connected here to the anode. So actually we are using the electronic breadboard. Then the center tap, which is 0, we are using 0.12 volts here. Okay, this should be connected to here. Okay, cathode is connected to one of the terminals of the resistor. Then the other terminal of the resistor is connected to this secondary winding of the transformer. Okay, now let us connect this oscilloscope. Positive over here. We will use this electronic board connector. Okay, one diode, transformer over here, secondary winding. The two terminals are connected to this input line. One of the terminal is connected to the anode of this diode. The other terminal is connected to this resistor over here. No? Okay. Then, this terminal here is the positive side. And this one here is the negative side. Okay, it goes like that. No? Half-wave. Only one of the half cycles is conducted. We have here. The output is only like that. Only that one. In one cycle, there are two half cycles. The positive half cycle and the negative half cycle. Only the positive half cycles is being allowed by this diode to pass because it is positive. No? That's why it goes like this. Half wave, because only half of the cycle. One cycle is composed of two half cycles, the positive half cycle and the negative half cycle. Since the first electrode that receives the voltage from the secondary is anode. During the first half cycle, the polarity at the secondary is positive and over here is negative. During the first half cycle, anode, which is positive, is in correct polarity with the supply voltage of the secondary winding. The secondary winding now serves as a supplier of voltage. It is AC. Remember, we measure the voltage there, it is 12 point something AC volts. So it is forward bias for this diode. This diode conducts. Now this diode is shorted, meaning very low resistance that allows the current to flow. from negative to positive because we are adapting electron flow. Now we have here the positive side and the negative side. Okay? During the first half cycle. But in the next half cycle, the polarity is inverted. This is now negative and this is now positive. Because actually, if we try to measure the frequency of this voltage here, set the digital multimeter to hertz for measuring the frequency. The frequency at the output of the outlet is 6 hertz. It is 60 hertz. In the secondary, it's still 60. See? It's still 60 hertz. Okay. Meaning, 60 hertz as a frequency, there are 60 cycles in 1 second. 1 cycle, 1 hertz. Two cycles. There are 60 cycles in 1 second. So, actually, frequency is the number of cycles per second. So, therefore, in the next half cycle, it is negative going. The polarity changes. Remember that AC voltage is not fixed in polarity. It changes the polarity for every now and then. How many times that the polarity changes in 1 second? Or there is 60 hertz? 60 times in 1 second. No? So in the next half cycle, it is negative going. The polarity goes like this. A while ago, it is positive. Now it becomes negative. Negative for the anode, it is reverse bias. This diode is considered open. Current is not allowed to flow because reverse bias. Remember, when you test diodes using ohmmeter, reverse bias, open, no pointer deflection. Forward bias, pointer deflects, meaning to say, closed. So diode serves as a switch for the flow of the current. So in this case, the negative half cycle is not allowed to pass. Then the next half cycle, it is changed to positive. Positive, negative, positive, negative. Now, for the third half cycle, it is positive. It goes back to the another polarity. Of this polarity, diode is forward bias because anode is positive. And the voltage at the secondary supplies positive volts. So, there is current flow originating from the negative to the positive side. There is a free flowing of current because diode is closed because it is forward bias. Again, there is voltage here. That's why it goes like that. It is half wave. It is half wave. No? From this frequency, okay, joules. Okay, it goes like that. We have here the complete cycles of the secondary winding of this transformer that provides AC volts. But at the output of this diode, we have here the oscilloscope test probe half only of the cycle. The negative half cycles are not allowed to pass. So, if only half cycle is at the output, that would mean it is already DC. DC. The AC is being converted into DC by this diode. Then, we can smooth out because when you supply that one to a certain amplifier or a unit to your cellular phone, to your amplifier, to your radio receiver, for example, it may cause distortion, hum sound. The music is accompanied with hum or distortion. So, because of this variation, there is still frequency at the output. No? We can measure the frequency at the output of this diode, that there is still 60 Hz. Okay? This is not the output line. The frequency here is 60 Hz. That manifests that there are 60 pulses. We call this one as pulsating DC. It is already DC, but there are pulsations. 12, 0, 12, 0. So the frequency is 60 Hz. 60 Hz actually is audible to the human ears. In the sense that the audio frequency range, which are audible to the human ears, are ranging from 20 Hz to 20 kHz. Those are the audible audio frequencies. And 60 Hz is within this audio frequency range. That's why we can hear that one as hum. In your amplifier sound system, the music, the voices are accompanied with hum because of this variation. So to minimize hum, we can use filter capacitor. Okay, we will connect capacitor to smooth out the pulsation. To smooth out the pulsation, okay? We'll connect here. Okay, this should be positive, connected to the positive side of the capacitor. Okay, we're here. We will connect this capacitor across this resistor. Then the negative side is connected to this side of the capacitor or of this resistor. Okay, we will use another. We'll use another connector. Okay. Then over here. A while ago, it goes like that. Pulsation. But when the capacitor is connected, the pulsating DC is now smooth out. There are still ripples, but at least the varying voltage is no longer 12. Instead, around 2 or 1 volt variation. Reducing the voltage will reduce the distortion or the hum that you can hear that accompanies the sound signal or the music, for example, or the voices. No, limited, reduce distortion, reduce hum because of this filter capacitor. Okay? How about if you are using Zener diode? Rectifier diode is used to convert AC to DC. It is designed to convert it, AC to DC. But we have here a Zener diode. What is really the operation or the function of the Zener diode? Zener diode is used as a voltage regulator. It actually eliminates pulsation. There is still varying voltage at the output of the supply filter capacitor. That will cause a little amount of hum because of that variation. There is still 1 to 2 volts variation. So, with regulator, the Zener diode will always provide a constant DC output voltage. No? Despite of the variation at the input. Because the voltage at the outlet is prone to variation. Oh, set it to AC. No? Prone to variation. It is not stagnant. The voltage changes for every now and then. This is 237.6. Now 237.7. For every now and then, the voltage changes. So despite of the changes at the input, the output is always a relatively constant output voltage because of the Zener diode. So, we have here a Zener diode connected in series with resistor. Okay, we have here a circuit with AC source, then the secondary, we have here the diode connected with capacitor, 330 microfarad with a working voltage of 25 volts. We have here a resistor with a resistance of 2.7 kilo ohms because the colors are red, violet, red, gold as a tolerance, so it is 2.7 kilo ohms. Then the Zener diode is connected here. There is a resistor and a Zener diode. You can notice, class, that the anode of the Zener diode, which is positive, is connected to the negative side of the rectifier circuit. With respect to the cathode of the Zener diode, which is connected to the positive side, that should be the proper connection of the Zener diode, because Zener diode operates normally at the reverse direction. It is always at the reverse direction. That is how we use and connect Zener diode in a circuit. So, the resistance of this resistor is 1 kilo ohm. Okay. Whatever the Zener voltage or the balance voltage of this Zener diode will be the output also of the power supply. Okay. Let us now connect. This positive is connected here and the negative is connected here. So, let us now measure the voltage at the output using this voltmeter. Set it to DC. Okay. Set it to DC. Then measure the voltage across Zener diode. 4.3 volts DC. The output or the voltage at the capacitor is higher, around 16 volts. But now it is being regulated to 4.3 volts because the Zener voltage of this Zener diode is 4.3. Because when you purchase Zener diode, you have to tell the Zener voltage. If the Zener voltage of the diode is 12 volts, then the output would be 12 volts. Although the input voltage is 16 volts. Okay? We will try to measure how much would be the voltage at the across capacitor. Okay? Again, DC voltmeter. Across capacitor, the positive is over here and the negative is over here. It is, let us first disconnect this Zener diode. .11 volts. It is DC. Okay. Okay. Okay, we are disconnecting this Zener diodes to make sure that the voltage across capacitor is accurate. The voltage is 16.3 volts. 16.3 volts across capacitor. Why is it that it is 16 volts? Since hence the voltage being supplied by the secondary is 12 volts. Okay, let us measure the voltage across secondary. The secondary voltage of the transformer AC is across secondary is 12.8 volts AC, 12.8 volts. 12.8 volts. Oh, Ayun, 16.8 volts. Again, let us measure it again. The voltage across capacitor is 16.4 volts. Okay? 16.4 volts. How come? Here's the voltage at the secondary of this transformer is AC. 12.8. It is 12.8 volts. Remember that the voltage that we can measure from the outlet or from the secondary is just an RMS. The root mean square, which is the effective value, the effective capacity of doing work. What we have measured from the outlet, 238 volts for example, is just 70.7% of the 100% peak value being distributed by the Solico company. That is only the effective value or the effective capacity of doing work. No? But it goes like this. It is just somewhere here. It is 70.7% only out of the 100% peak value being distributed by the Solico company. And it is only 12.8 volts. That is measurable by our tester. However, how come it reaches to 16.4 across capacitor? Remember that capacitor will always store voltage up to the peak value of the amplitude. So, how much would it be peak value if this is 12.8 volts being measured from the secondary winding? So, try to get the peak value. Peak value is equal to RMS times 70.7%. Oh no, 1.414. Remember, 1.414 is a constant value given. RMS now is 12.8, the root mean square, which is measured from the secondary, which is only 70.7% of the 100% peak value of the amplitude, times 1.414. Compute. Try to compute. So, 12.8 times 1.414. This is 2, 3, 11, 5. Sure, we will use a cellular phone. That was 12.8 times 1.414. The result is 18.09. 18.09 volts is the peak value. No, 18.09 as the peak value. So, this is now the voltage at the output of the capacitor. Okay? We will measure that one again if it is really 16.4 volts. So, DC. Okay. Negative here, positive here. $16 volts because diodes and other components drop voltage. So the remaining voltage now is 16.4 across capacitor. It is DC. DC, it's DC. But with zero diode as a regulator, what happens? Okay. Here, Okay. We will now connect the Zener diode. What's this? Okay. What's this? Connected. Would be the voltage across Zener diode as a regulator. Let us now proceed here. Alright class, let us now proceed to the next rectifier circuits, which is full wave rectifier circuits, center tap type. Okay? Let us dismantle this one to assemble a center tap type of rectifier circuits. Okay? A full wave rectifier circuit uses two diodes. Okay? Uses two diodes. It goes like this, class. The three terminals of the signal winding are now applied or used 12, 0, 12. No? We have here 0, 12, 12. Then, two diodes are being used. Designated as D1, diode 1, and you have here diode 2. Then, the two cathodes are connected together. Then we have here a resistor at the output. Okay? That serves as the RL or the load resistance. We have 2.7 kilo ohms for the load resistance. The two anodes actually are connected to the two terminals of the secondary winding. We have here. The other terminal is connected here. Okay. So, we are now connecting the two anodes of the diode, no? The anodes, okay? To prove that these are anodes, we will measure using, because the white band of each diode is no longer clear to our eyes. Okay. The two anodes now are connected over here. Let us first disconnect the power supply. Now, connect. The two cathodes are connected together. The two cathodes are connected together and connect it to the resistor of 2.7 key. Whereas, the other terminal of the resistor is connected to the center tap. Which is this one here. No? Center tap. Okay, we have here. Okay, just like that. And connect it here. Now, without our capacitor yet, we will connect this one across RL. What will be the waveform? What will be the waveform? Okay. Also, this will be connected to the secondary. Winding. Supply it with voltage. So, it goes like that. This one here is okay. This AC waveform now, which is 16 volts peak value, and the RMS is 12.8 volts, is at the output of the secondary. Whereas this one now is at the output of the diode across resistor. It is full wave. It is full wave. And if we try to measure the frequency of that, if we try to measure the frequency of the output using a frequency meter, it is 60 hertz. Oh no. It is not 60. There's something wrong. Okay. We will now measure the frequency across resistor, which is now the output of the rectifier circuits. It is 119.8 or 120 hertz. The frequency is doubled because the frequency at the input is 60 hertz or 59.8 or almost 60 hertz. But at the output of the rectifier circuits, it is doubled. The frequency is 119.7 hertz or almost 120 hertz. Actually, a full wave rectifier circuits center tap type is a frequency doubler. Frequency doubler. Oh, key wave here. Why it becomes full wave? Because it goes like this. In the first half cycle from the secondary winding, by the way, the transformer is a center tap type. Dual output voltage, because dual, meaning to say there are two output voltages which are opposite in polarity to each other. No? Okay. AC, using AC voltmeter. Measure the voltage here. It is 12 point something. Measure the voltage here. It is 12 point something. So, split power supply. Dual output because there is output voltage from 12 to 0 and another 12 point something voltage from 0 to 12. It is a center tap type in the sense that there are three terminals at the secondary winding. Okay, it goes like this. Why it becomes full wave at the output, and it is 120 hertz. So, in the first half cycle, this must be positive here, and this center tap is negative. Then, the center tap is positive, and this should be negative. These are the dual output voltage. This is like this, and the other one is like this. The output voltage of the center tap here, towards here is negative going. Whereas, the center tap here, negative to positive, is positive going. Dual output, simultaneous output voltage. Okay. And this first half cycle, which of these two diodes is conducting? Diode 1 or diode 2? It is diode 1 because secondary voltage is positive over here, which is connected to the anode of this diode, diode 1. This diode conducts. It is closed because this diode is reverse bias because the secondary voltage polarity is negative. Then this one is anode. It is reverse bias. It is open. Whereas this one, anode, then positive, it is closed. It is forward bias. So, the flow of the current goes like this. It starts from the negative. Since this diode is conducting, so we will focus on this polarity. Negative at the center top, over here, because we are adapting the electron flow. In our module, the diagrams use photon flow, but it is inverted here because we are actually in electronics technology. We are adapting electron flow. Even the electronic books that we have here in electronics shop, no? So, from negative, center top, going to the load resistor, then going back to this positive side. So, for bias, the output is like this. There is no current flow of this diode because it is reverse bias. But, in the next half cycle, which is negative going, the polarity changes. Positive, it becomes negative, and negative becomes positive. So, reverse bias already, and the negative half cycle, which is the next half cycle. This diode now is not conducting because it is reverse bias. Negative anode is positive. Then, here is negative, changes negative to positive. So this diode is conducting because the polarity now is changed to positive. This is conducting. So the current would flow like this, going to the resistor, then to this side. This is not conducting, this is conducting. So the two diodes are alternate in conduction. This diode conducts 60 times in 1 second. For there are 60 half cycles. There are 60 positive half cycles. And there are also 60 negative half cycles. So both diodes operate alternately. They are not operating at the same time or simultaneously. No? So they alternate. Off, on, off, on, off, on. The on and off, this diode turns on and off 60 times in 1 second. 60 times in 1 second. That's why the output goes like this. So, the negative half cycle is converted into positive. No? So, double frequency, 120 Hz. Now, if we connect the capacitor across this resistor, okay, positive is here and negative is here. The result is like this, positive here and negative here. Okay. Alright class, we are now connecting the oscilloscope test probe across this capacitor here to determine the position of the output. It becomes like this. This is now varying compared to like this. That is now half-wave rectifier circuits because we are disconnecting the one of the diodes. This rectifier circuit is operating half-wave and the varying voltage at the output of the capacitor going like this. But if we are using full wave, it is refined. So therefore, among these two rectifier circuits, half wave, the first rectifier circuits that we assembled, compared to this full wave, it is advantageous to use full wave center of type in the sense that the varying voltage is refined. No, refined. Unlike a while ago, there's a bigger pulsation or bigger varying voltage. Probably there is a variation of 2 volts. But with full wave, with full wave, alright, this is now the difference between half wave, bigger variation, around 2 volts variation, but full wave, the variation is refined. The variation of the voltage is around 1 volt compared to half wave, which is 2 volts. So, when it is supplied to a certain amplifier sound system, the sound is better than half wave because the sound now is less in distortion for the full wave compared to the half wave, which is bigger variation of voltage around 2 volts. But with full wave, it is refined, it is 1 volt. So, in other words, it is advantageous to use full wave for both half cycles are being passed. So, the efficiency is higher, the power is greater than half wave. Because in half wave, only half of the cycles are allowed to pass. But with full wave, both half cycles are being passed, thus giving higher efficiency. No? Aside from that, the frequency is doubled from 60 to 120 Hz. Okay? That was all about full wave rectifier circuit, center tap type. Okay, let us now come to the full wave rectifier circuits, bridge type. Last type of rectifier circuits, which is bridge type. Bridge type uses 4 diodes with the same transformer. Okay, 0, 12. So we have here, we are using 4 diodes. So it goes like this. And we have here the load resistance over here. Diode 1, diode 2, diode 3, diode 4. So, a little bit complex in the sense that we are already using 4 diodes. So, we have here a circuit here. Okay. Only 2 terminals of the secondary winding are being utilized. Here, and the other one is here. Okay. Then, let us get the output. What will be the output signal waveform? Again and again, let us connect the oscilloscope test over here, whereas this one across the resistor of this bridge rectifier circuits. Okay. There's something wrong with the circuit. Turn off. Dismantle. Okay. Anode. Okay. You have here. Let us disconnect first this one. So, the 2 terminals of the secondary winding is connected here. Over here to the cathode anode combination connected to the one of the terminals of the secondary winding. No, they can be inverted in any direction. It can be interchanged because the output voltage is AC. No? Cathode, anode, cathode, anode. Okay. Then, the anode here is connected to the resistor. We'll connect resistor. This one. This one. Connect resistor as the load. Then this is negative. So we have here the negative. Then the positive is over here. Let us connect this one here. Then finally, this is connected here. Then we'll connect the oscilloscope test probe across this resistor. This resistor. Okay. Then let us recheck it again. So anode connected to this positive, cathode. Okay, let us try to connect. There is something wrong. Anode, cathode, anode. Anode is negative, connected here. Then cathode are being connected together here. Then we have here the resistor across this resistor. So we are using this transformer. B again, let us try. Oh, there's something wrong. B. The positive side here. Then this one here. To this one here. Then connect it here. Connect it here. This one here is across. Half wave.